Welcome to the fourth video in the linear algebra series. In the last videos we introduced some basic concepts in matrix theory. So we first defined the linear system of equations, then we talked about Gauss-Jordan reduction and then matrix algebra. And now we want to, in a way, combine the last two sections that we covered. So we'll talk about a more abstract concept, which is the concept of non-singularity, which in a way relates to Gauss-Jordan reduction. So we first want to motivate why you're interested in this topic. So the question that we have is, when does our linear system, LEAB, have a unique solution? So we saw before that this linear system, so if you have identity matrix and B is an n vector, then it has a unique solution, which is the solution x is equal to B. So we let A be an n by n matrix. If there exists a matrix B such that BA equals I, then it has a unique solution. Namely, we can take the linear system that we had before. So we have AX equals B, and we simply multiply from left and right by B. So how that looks, we have BAX is BB. And because this is identity, what you can show is that identity times x is just x. We obtain the solution x is AB, which you also see here. So if we can find such a matrix B, then we see that our linear system has a unique solution. And this motivates us to investigate for which matrices such B exists. And this leads us to the notion of non-singularity. So we first need to cover some other details though before we get into this. So we say that the matrix is called square if it has the same number of rows as columns. So in this case, our matrix A was in n by n, so it is a n by n square matrix, or we just say let A be a square matrix. Okay, the n by n identity matrix I is the matrix defined by this. So this might look a bit confusing at first, but if you think about it a bit more, this condition here just basically means if you are on the diagonal, you are 1. If you are not on the diagonal, you are 0. So for example, we have example here of a 2 by 2 identity matrix, which is this one. And you also have a 3 by 3, 4 by 4, etc. of course, because we can take any arbitrary n. Then another theorem that we have is that multiplying a matrix by the identity matrix just leaves it unchanged. Doesn't matter if you multiply from the left or from the right. So in this case, it does commute. Yeah, so if A is in n by n, we need to note that for multiplication to work, we need to check that the number of rows is equal to the number of columns. So this needs to hold, and this needs to hold. So and these are two different identity matrices. Okay, now we can define non-singularity. So let A be a square matrix. We say that A is non-singular if there exists another square matrix of the same size, B, such that AB is identity and BA is identity. This matrix B, we call it the inverse of A, and we denote it by this, so A to the minus 1, so A inverse. If no such B exists for a given A, then we say that A is singular. So we can see an example now of a singular matrix. So this matrix, the 0 matrix, 2 by 2, any 0 matrix will be singular, sorry. It is singular because if we take an arbitrary matrix, so this A, B, C, and D, they can be any real or complex number, it does not matter. If we multiply this, we see that we obtain 0, 0, 0, so the 0 matrix again, which is obviously not the identity matrix. So there does not exist a B, a 2 by 2 matrix B, such that the 0 matrix times B, or the other way, is identity. So this is a singular matrix. So now we have some more concepts regarding non-singularity. So they relate the products and other operations of non-singular matrices. So let A and B be non-singular. Then the inverses of A and B are unique. So A inverse and B inverse. AB and BA are also non-singular, and we can see this because we can, in a way, take out the exponent when we take the inverse, and you have a similar property here that you had to the transposes. So we have that the inverse of AB is B inverse times A inverse, and the inverse of BA is A inverse times B inverse. And the way you can see this, if we have AB and we multiply it by B inverse A inverse, by the definition of an inverse, we will see first that this BB inverse reduces to identity. So as we saw in the theorem before, multiplying by identity leaves the matrix unchanged. So we are left with this. But this is also identity, because A times its inverse is identity. So this matrix is indeed the inverse of AB. And the same method of reasoning holds for this product. Oh yeah, and then we need this definition. So if we have a linear system like this, Ax is equal to 0, so this is a particular case where B is 0. We say that the solution is trivial if it is the 0 solution, so x is 0, and any solution not satisfying this condition is non-trivial. So keep in mind though that 0 here means a column vector of zeros of the correct size, also in this case. Okay, and now there are some equivalent conditions for non-singularity. There are many more, but here we just covered the first few. Let A be a square matrix, then the following are equivalent. So that means if any of the conditions is satisfied, then all the others are also satisfied. First one is A is non-singular. Okay. Then we say Ax is 0 has only the trivial solution. For any B, a solution to Ax equals B exists and is unique. And the row-reduced echelon form of A is identity. So I will not prove these properties, but accept property number 2, because I think the proof is nice. So suppose that we indeed have Ax is equal to 0. Then since A is non-singular, that is our assumption, we want to show that A is non-singular implies this. So A is non-singular, then we can take the inverse of A and multiply from the left, like this on both sides. The left-hand side will reduce to x, and the right-hand side is just 0. So we have shown that Ax equals 0 implies x equals 0. So indeed Ax equals 0 has only the trivial solution. Okay, that was a short section on non-singularity. I hope you enjoyed the video. In the next section we will look at determinants and some other, we will see that they also provide an equivalent condition for being non-singular. And yeah, thank you for watching. See you in the next one.